a model type theory of expected cost in higher order probabilistic programs, presented by Vineet from University of Kent.
Hi everyone. In this talk, I will describe a modal type theory for expected cost analysis of higher order probabilistic programs. My name is Vineet Rajani and this is joint work with Gilles, Barthe and Deepak Garg. So, abstractly speaking, we want to build a logic to reason about expected cost properties. Examples of such properties include bounds on expected loss or regret of prediction algorithms. Needless to say, such properties are of great interest in the machine learning community. Let's look at a concrete example. Here is a simple but a fundamental problem from the online learning literature called the experts problem. Basically, it's a prediction problem where the prediction is to be made using a bunch of experts. The task is the following. Every day, the algorithm needs to make a prediction about some event like the likelihood of a rain today or the price of a stock going up or down or something like that. To make this prediction, the algorithm can seek advice from a bunch of experts and finally make its own prediction based on their advices. One popular algorithm for this problem is called the randomized weighted majority, or RWM for short. As the name suggests, this is a randomized algorithm or a probabilistic algorithm which takes the following inputs. Number of rounds to run this algorithm for, which is a NAT, a list of experts, which are functions from NAT to bool. Now just for simplicity, I'm assuming that the experts make a Boolean prediction here, but it could be more general than that. The algorithm also takes a list of weights as inputs, which the algorithm will use to assign weightage to the experts, and finally a learning rate, which is a real number. Now those were the inputs. What will the algo produce? Well, it produces a distribution over the list of predictions made in all the rounds. Now I have already taken the liberty to denote the distribution using a monad here, thanks to Michel Jarry for showing that the probability distributions have a monadic interpretation. Okay, now let's look at how this algorithm works. Well, if the number of rounds is 0, there is nothing to be done. You just return a point distribution on an empty list. Otherwise, you get the advice from all the experts in that round, then make the prediction based on their advice. The way you do that is you compute a uniform distribution over the weights, sample from that distribution, and go with the advice of the chosen expert. After that, you get the true answer from an oracle. Based on the answer received, you calibrate the weights of the experts. Experts who got the answer right, you don't change their weights. And for others, you reduce their weight by a factor of 1 minus eta. And that's it. After that, you just recurse until the end of all the rounds and ultimately producing a distribution over the predictions. Now, this is a higher order probabilistic algorithm, as we saw, and there is no guarantee that every prediction is going to be correct. So a natural question that arises at this point is, can we bound the number of mistakes that this algorithm can make in expectation? Turns out we can. Specifically, we can show that the expected loss over capital T number of rounds is bounded by the difference as shown here, where phi t is the sum of the weights of the experts in round T. So now the question is, how do we actually prove this? Well, proofs of this kind of theorems are often done using a ranking function based approach. What are ranking functions? Well, ranking functions are just functions from the program state to a positive real number which satisfy certain properties. Now, some of you might have heard of ranking functions like ranking supermartingales, which are often used for termination analysis of probabilistic programs. But there are also potentials, which are often used for cost analysis, and that is what we are interested in. Now, as far as I know, potentials or the method of potentials was originated in the amortized computational complexity literature. And the key idea is basically the following. So you choose a potential function phi such that the cost of the ith step is upper bounded by the change in potential from the ith to the I plus 1th step. And then you just telescope over the n rounds to obtain a bound over the total cost as the difference between the initial and the final potential. In effect, the method of potential allows you to pay for the cost using some credits which are called as potential share. Now the advantage of this is that in some cases you can derive much more precise bounds than using direct worst case analysis. And also for some problems it is sometimes simpler to come up with a potential function than coming up with a direct cost bound that can be proven inductively. Now for the problem at hand, it turns out choosing log phi t by eta serves as the potential for the round t. Now if you do some arithmetic, you can show that the expected cost of the tth round is upper bounded by log phi t by eta minus log phi t plus 1 by eta, exactly that we desire. And then you can prove the theorem that I showed you in the previous slide. Okay, so that's how you prove this theorem, but what's the research question here? Well, the research question that excites us is how can we build a logic that can be used to prove these kind of potential based bounds? And that's the goal of this project. So we achieve this goal by building P lambda amor, a graded modal type theory for proving these kind of bounds. P lambda amor builds on our prior work from POPL 21 called lambda amor, where we tackled a similar problem of cost analysis in a deterministic setting. Now there are several ingredients that go into building P lambda amor, and today I will only talk about two of them, graded modalities and probabilistic coupling. Now there are three graded modalities in P lambda amor: a graded monad, which is a doubly graded version of the Gilles monad of probability; a modality for capturing potential, which is a reinterpretation of the potential modality from lambda amor; and a graded comonad, which is a refinement of the comonad from bounded linear logic. Let's look at the first modality, the probability cost monad, or PC monad for short. So the PC monad is graded with mu, which is a symbolic distribution over static indices like natural numbers, and kappa, which is an upper bound on the expected cost of a computation of this type. Now, I just want to mention here that the actual monad in the paper is a bit more refined, as I have shown here in the footnote. It allows a variable a denoting a sample from the distribution mu to appear free in tau. But I will ignore that refinement in the remainder of this talk for the sake of simplicity. Okay, now let's look at the return and bind of this monad. Well, return just takes a non-probabilistic and cost-free term E and puts it into the monad. As a result, it grades the monad with a point distribution and a zero cost. Now bind is a little tricky. Bind describes composition of two distributions where the second can depend on the first. So basically what happens in bind is you sample a value from the first distribution mu1, and for each such possible sample you analyze the continuation E2, thereby giving you a probabilistic tree of computations. And that is why mu2 and kappa2 are not a single distribution and cost, but a family of distributions and cost indexed by every value in the support of mu1. And this is the reason why the distribution in the conclusion mu is the convolution of mu1 and mu2, and the cost in the conclusion kappa is the sum of kappa1 and the expected cost of kappa2 taken over mu1. Now there are a few things that I'm pushing under the rug. The actual rule that we have in the paper is a bit more complicated, but we can ignore those things for now. Okay. Now only return and bind are not sufficient. We also need a construct to define cost models, like counting the number of mistakes in our RWM example and so on, right? And this is where the tick construct comes in. The tick denoted using the up arrow kappa is purely for the purpose of counting cost here. As a result, the type of tick is a monad over the unit type graded with a point distribution and kappa cost. Okay, now let's look at the effect of the PC monad on this type of RWM. Now on the left hand side, you can see the type before from before, and on the right hand side is the new type. Now I want to zoom in on the type of the prediction, the result, yeah, because that's the most interesting bit here. The type now is a lot more informative. It tells you that the expected cost of obtaining a bunch of predictions is bounded by the logarithmic term as shown in the type. Now this is already a huge improvement from the type before on the left hand side, which gives us no information about cost or probabilities whatsoever. However, there are still two problems. The revised type still doesn't give us the bound of the theorem from before. It was a difference bound, remember? So this bound is not very precise in that term. And second, we need to quantify over a distribution mu here, which is a problem because now we have to compute a convolution in order to even type check RWM. Now, computing such convolutions can be quite complicated, especially for higher order recursive programs like RWM. So to handle this problem, we make use of probabilistic couplings. Now, couplings are a standard technique in probability theory, which allows you to reason about a pair of distributions together instead of reasoning about them individually. As a result, couplings have found a good use in the verification of relational properties. However, our use of couplings is very different. The key idea that we have is we have a rule in the logic which allows you to coerce a complicated distribution to a simpler one as far as there is a coupling between the two. Now, prior work from LIX 19 makes similar use of couplings. However, LIX 19 takes a very different approach to cost analysis. It is a co-effect based system and does not use potentials, while P lambda amor takes a effect based approach and uses potentials. I will talk a bit more about the relationship to LIX 19 in a second, but let's first understand the effect of this rule on the type. So, well, what this coercion allows you to do is it allows you to simplify the distribution without changing the bound on the type. Yeah, as a result, we can get rid of the problem of quantification over mu and hence the need to compute those complicated convolutions because we can immediately coerce them to something simpler. This is reflected in the revised type of on the right, where we replace mu with a point distribution by showing a trivial coupling between them. Now this is great because it drastically simplifies the verification effort, which is key to verification of such real-world machine learning algorithms. Next, to reason with potentials, we introduce a new modality that allows you to attach potential with types, denoted using this bracket construct here. So we enter this modality with two operations, namely store and release, which is what allows you to pay for the cost using potentials. Now store, the store construct, it's similar to return. It takes a pure term and puts it into the monad. However, unlike return, it allows you to store k units of potential with the type. And also, unlike return, store is a costful operation, as storing k units of potential requires k unit of cost, while return was an operation with zero cost, right? What about release? Well, release is the dual of store. It takes a term with k units of potential and makes it available to its continuation, which has a cost of k plus k prime units. Now, since k units are paid off using the potential, the remaining k prime units must be accounted for as an unpaid cost, and hence it shows up as the cost in the conclusion. Now, you might be wondering, why is this rule sound intuitively? Well, this kind of a partial payment of expected cost using potential works out because of linearity of expectation, and this is internalized in the semantic model of our modalities. Okay, so now let's revisit our example again and see how the potential changes the type of RWM. So now RWM takes an additional argument for the input potential, namely IP, and also returns back the remaining potential, namely RP here. And the rules of the type system will make sure that the cost of RWM in each round is bounded by the difference of IP and RP as desired. Now this is also reflected in the type, as the remaining cost is now 0 units because the input potential is enough to pay for the cost, which is exactly what we want. So essentially we have seen everything that is needed to reason about cost using potentials now. Now very quickly, let's just talk about the relation between these two modalities that I've shown you. So we have seen two ways of reasoning about cost. One is a direct way of accumulating cost using the cost monad, shown by the type here. And there is a second way, which is an indirect way of paying for the cost using the potentials, which I have shown here using a function type, which takes k units of potentials and returns a computation which has no additional cost. So now the question is there a formal way to relate the two modalities? Well, turns out if you have a term of the left hand side type, it can be coerced into a term of the right hand side type and vice versa. And additionally, the composition of these coercions gives you an identity. As a result, the two types are actually isomorphic. Now this isomorphism is not only interesting from a meta theory point of view, but also plays a crucial role in the embedding of LRPCF, which is a co-effect based system, into ours, which is a effect based system. Finally, I want to briefly touch upon the semantic model and the soundness bit. Like many modal logics, we build a possible world model of probabilistic lambda amor, which we encode using the technique of Kripke step index logical relations. Now in the model, we define another coupling, which is a coupling between the static and the dynamic distributions. Now this is required to prove the soundness of the coupling rule that I showed you earlier. And then we use this model to prove the soundness of P lambda amor, which basically states that if an expression is well typed, then it will adhere to its cost bounds. Additionally, we can also show that the runtime and the static distributions can be related via a coupling. Similarly, because of the isomorphism I showed you earlier, we can also obtain same guarantees for the isomorphic type. So to end my talk, I just want to mention a few additional things that are in the paper, but I did not talk about. So there is a third modality in the paper, which is a graded comonad. And we also describe its interaction with the potential modality via distributive laws. And also there are more examples from the machine learning literature, like bandit problem and the stochastic gradient descent. And that's it. Thank you very much. Thank you for listening.